So I'm coming with these are my group members. So a short introduction to the BST is that they are fundamental in computing and that they organize elements in a sorted manner and that they follow efficient operations and time complexity. So in this scenario here, our binary search tree evaluation with AI chatbot will be focusing on the emphasis of accuracy, completeness, clarity, and relevance. We'll also be looking at the advantages, disadvantages, and the real-world applications. So a short look into binary tree versus a binary search tree properties is that for binary tree is that every node has at most 2 children on the left and the right, and there is no specific order between the nodes. And for the binary search tree is that the nodes will follow an ordering property where a smaller value will go to the left and the higher value will go to the right. So some of the key questions are asked here regarding the properties that define a binary search tree and how do they differ from a regular binary tree, and the time complexity of insertion, deletion, and search. And this is the ChatGPT's response. And following that, what we have evaluated from the ChatGPT response is that it gives the right differences between a binary tree and a binary search tree. For completeness is that it covers the key differences. For clarity, it gives clear and concise explanations with minimal jargon. And for relevance, it is highly relevant for learners or developers needing a quick conceptual comparison.
Now we'll be looking into the impact of tree height on BST. So first of all, what is exactly the height of a BST? So the height of the BST is basically you start from the root, you follow the path with the most number of edges, and basically the last node gives you your height. So based on this, we wanted to ask 2 main questions to ChatGPT. First being, how does the height affect the performance of BST, like insertion, deletion? And why do we need our BST to be balanced like this image over here and not unbalanced like this image over here where it's kind of skewed? I'll answer this question in a while, but first let's look into the response that ChatGPT gave us for the first question. So basically ChatGPT is saying that if you have a taller, more unbalanced tree, it will be slower, of course, and if you have a more ideal kind of tree, like the one over here, you'll get a complexity of O log n for insertion, deletion, and searching. So now let's evaluate the answer. So basically we can definitely say the answers that GPT gave us is accurate, because if we look into the 2 different graphs, if you have O log n complexity like this balance tree, of course it'll be easier to find 7. But if it's a skewed graph over here, to find 7, it has to look through all of them, then it will find 7. So of course what ChatGPT said was absolutely accurate. But what ChatGPT was missing was in terms of completeness and clarity. Basically, ChatGPT didn't give us any idea about what about the memory space complexity. How does it affect the memory space? It didn't say anything about it. Not only that, it also didn't give us the worst complexity that I just mentioned. It didn't talk about the O n complexity. It just said that the ideal is O log n. However, not only ChatGPT missed out on completeness, it also missed out on clarity. There was no clarity in the idea. So he gave the main idea, but there was no visuals for us to see how it works. Also, no specific examples were given. That is why we would say in terms of clarity, it also didn't really hit the mark. And the only part that I would say ChatGPT did well was in terms of relevance. I think that all the information that were given was related to BST. Now moving on to the next question, where we ask why a balanced tree is important and how an unbalanced tree will impact, is the same idea. So as I mentioned, if you have O log n, basically the time complexity will be really shortened. So what he's trying to say here is that if you have 1 million nodes, to find one node will take you around 20 steps if it's O log n, where it's a balanced tree. But if it's a skewed tree, to find one node, maybe it will take you 1 million steps because it's all the way at the bottom. So that is why a balanced tree needs to be balanced. A BST needs to be balanced in terms to increase efficiency. So I would say this response was much better than the response that we get earlier. In terms of accuracy, he gave the correct information. It was a more complete answer where he gave real world examples, and it also talks about the different parts like the space complexity, the caches, and whatnot. And it was very clear. It clearly conveyed the message this time. However, still, it was missing the visual impacts. There was no visuals. And it was very relevant, all the information that also it gave. So this was a much better response. So that is all.
Hello, everyone. I'll be discussing BST degradation and avoidance, focusing on how balancing affects performance. I'll also reflect on the usefulness of AI chatbots in understanding these concepts. A BST is efficient when balanced, allowing for a O log n performance. But if unbalanced, it can degrade to an O n performance, making operations slow. A BST degrades when elements are inserted in sorted order, forming a skewered structure that resembles a linked list. For example, inserting numbers in ascending order creates a right skewered tree, making searches inefficient. To avoid this, we can use self-balancing BSTs, such as ABL trees, which maintains a strict balance with frequent rotations. A red-black tree can also be used for a more relaxed approach with fewer rotations. We can also use randomized insertion and periodic rebalance to help maintain efficiency. ABL trees offer better search performance due to its strict balancing but requires more rotations. A red-black tree is faster for insert and delete functions because they balance less aggressively. Choosing between them depends on whether search or modification speed is more important to the user. Upon using these AI chatbots, they help me understand these concepts quickly by providing structured explanations. They are also great for initial learning, but they do have their limitations of oversimplifying details and lacking real-world context. So while AI is indeed a useful tool, critical thinking and further research is also essential. I'll now be passing my time to my group mates for the next topic.
So finally, we explored the strengths and weaknesses of BSTs and the restrictions that come with using them. So our interaction with ChatGPT was, what are the advantages and disadvantages of BSTs? And are there any specific restrictions in their use? The chatbot outlined several advantages such as efficient search operations, dynamic size handling, and in-order traversal for sorted outputs. It also mentioned that BSTs are memory efficient compared to arrays and suitable for dynamic datasets. On the flip side, the chatbot noted that BSTs can become imbalanced without proper handling, leading to degraded performances. It also mentioned drawbacks like memory overhead from node pointers, lack of thread safety, and the implementation complexity of self-balancing variants. Furthermore, the chatbot emphasized the requirement for unique and comparable keys, and they also explained how duplicates need special handling, as well as how other data structures like hash tables may be better for constant lookups. For the evaluation part, the chatbot responses was comprehensive and well-structured. It highlighted both the theoretical and practical aspects of BST usage, such as efficient search, dynamic sizing, and imbalanced trees. However, the evaluation would be stronger with examples of use cases where BSTs outperform or underperform compared to hash tables or arrays. Still, the response provided a balanced view of BST suitability in real-world scenarios.
The application we have created is a binary search tree visualizer built using PyQt. It helps users understand the BST operations by animating insertion, deletion, searches, and traversals. The primary data structure used in our code is, of course, a BST, represented in the code by 3-node class. The remaining code is structured with modular functions handling specific operations or features, including functions like tree manipulation, traversals, visualization, under a bigger class called BST visualization. The core operation insert, delete, and search are animated step by step. The insert finds the correct position and places the node. The delete adjusts the tree structure based on different cases, leaf node, one child, or two children. Search highlights the path to the node, and draw tree function. The tree is drawn dynamically using PyQt, updating in real time as operations are performed. Our secondary function in the visualizer supports in-order, pre-order, and post-order traversals. Here, nodes are highlighted sequentially, helping users see the exact order in which tree is traversed. This feature makes it easier to understand how BSTs processes data. Our miscellaneous feature includes speed control of the animations, viewing operation logs of the steps taken and comparisons made, and UI controls to manipulate the tree with good visualization. These enhancements improve the learning experience by making the visualizer more interactive and user-friendly.
Hello, and this is our BST visualization application. There are two ways of generating a BST with our application. You can either manually insert your values. Let's insert 50. Then now let's insert, let's say 20s. And now let's insert 80. As you can see, this one we are generating a tree. You can also generate a randomized tree. And with this an example, we can use the other functions such as search. Where we will cycle through the entire BST looking for the number, and they'll tell you whether they have found it or not. Along with the search process, they'll also tell you that the steps taken. So let's say we look for the number 16, right? You'll say that 16 is smaller than 81, go left. Smaller than 71, go left. Smaller than 29, go left. And so on and so forth until it has found the value. But what if in the case that we look for a value that is not in the tree? So let's say we put search 15. You'll go through still the same processes, but you also come to a realization that 15 is not found in the tree. Now, along with the search process, we can also use it to delete numbers of the tree. So let's say you take the number 16, for example, we can also delete it. As you can see, it's just along the same process, but deletes it at the end. Along with this, we are also able to find the in-order traversal, pre-order traversal, and the post-order traversal. As you can see, there's a animation that highlights how the traversal works. If it's too fast for you, you can increase the speed taken in between traversals and in between animations that you can see. You can visualize it more clearly. On the other hand, if it's too slow, you want to cancel it. You can cancel, increase the speed, decrease the speed. We also included a button to cancel the animation and then adjust the speed. Other functions that we also added is the clear tree function. You can randomize, zoom in, zoom out. If the tree is too big, make the tree less compact. So clearer visuals, and also toggle in between light mode and dark mode. And that it is for our BST visualization application. Thank you.